Hello and welcome back to Let's Code Physics. I am excited to share some developments with you in our self-driving car simulator. You can tell we've got some different visuals over here in the scene view because I've found a better way to do a visualization of the lines along which our cars are looking for each other. You also notice it's moving faster. I just decided to change the speed limit on this lane so that I could test it a little bit faster. You also notice that our cars are not running into each other anymore because we've successfully implemented both a slowdown and a speed up for the cars to be able to follow each other more successfully. First, let's talk about this difference in how the cars are looking for each other. So last time I was using this function raycast, where you have to specify an origin, a place for the ray to start, and a direction for it, which is fine, but that means you have to calculate the direction based on the 2 points that you want to look at, which is what I was having to do over here. So I did a little digging and I found this drawLine function that just takes the 2 points as the inputs, and it takes care of calculating the direction and everything. It's always better to use native functions to the system because that's going to do it more efficiently than my calculations up here. Also, I changed for the debugging. I changed the draw ray into a draw line, and that's drawing from one point to another. The rest of it works the same way. We're still getting out the information about whatever the line hits, and that tells us whether the line sees a car, whether it sees a building, etc. Right now we're just checking for car. I don't have any buildings in the world yet. We will be adding those in the future. The other thing that I've added is a physical calculation of the stopping distance. So before I was just doing an estimate of the number of car lengths. It worked fine for getting the logic below set up. But what I've done here is I've used the kinematic equation v final squared equals v initial squared plus 2ad. And we've just solved that for the distance that the car would need to stop. We're taking the car's current speed and squaring it. We're dividing by 2 times the braking force. Really, this is an acceleration. But later on we might make this an actual force and then divide it by the mass. And then we're adding on the length of the car, because if we just do this part, it considers the center to center distance, and it doesn't take into account the fact that we've got a distance from the center of the car to the edge of the car here. And so we were getting the 2 cars playing bumper cars, and they technically weren't colliding because they were following at the stopping distance, but the stopping distance was less than the width of the car, or length of the car. Technically this only needs to be half, but I figure I'll, better safe than sorry. And then we're multiplying that by 1 plus our stopping safety factor. I believe the safety factor, let's see what it is. Safety factor is currently 0.2, so it's a 20% safety factor. So we've got an additional 20% of distance that we don't technically need, but that we, we'll have. And we can play around with that to try to balance between the safety considerations and getting people to their destinations on time. Then I've also had to define a following distance. This is the stopping distance plus another 20%. So this is the distance where if one car is behind the other car by this much distance, then it's not going to try to accelerate to catch up, but it's not going to brake to try to stay away. This is the ideal distance that the cars are trying to stay between each other. So, for example, right now the cars, I believe, are maintaining a pretty constant distance from each other. The speeds are not varying by much. So they're not. Yeah, the speeds are not varying by too much here because they're basically maintaining that following distance between each other. Let's see, what else have I done since last time? Okay, I changed the logic here a little bit, where we are always going to evaluate the distance between the 2 cars, even if even if you don't necessarily need to slow down, because we do want to be able to know whether we should follow the car. I've also changed the logic of evaluating slowdown. So before I was evaluating comparing their velocities and comparing the distance with the stopping distance in separate lines, and that was causing too many exception cases where the car was not obeying the way you would expect it to, and so I've just moved those into a single line here. So these are the two factors for considering whether the car needs to slow down. I've also added in, I wanted to have some print statements about what the car that is trailing is doing. So I've added in a logical variable do debug for true if we want the car to be printing debug statements, and false if we want it to not be printing debug statements. So our slower car, the car in front here, has do debug turned off because its speed limit is going to be pretty consistent because it's not going to feel the need to slow down for the car that is behind it. And so this car has do debug turned on. So all these numbers that you see are from the car that's initially traveling faster than this car. And then the biggest thing that I've added is an adjustment of the car's speed in the upward direction. So last time we were able to get the car to brake, but of course if the car in front, turns off the road, we want it to be able to accelerate back up to its preferred speed. And so we've got a couple of scenarios here. One in which, if we're within the following distance, we try to match the speed of the car. And we've also got a scenario in which the car speeds up. So let's say the car in front speeds up and the car behind can speed up as well. Basically what this chunk does is enables us to have the car in the back following the car in the front and matching its speed. So they become coupled as if they were train cars. And that's basically what's happening here. They're maintaining a fixed distance between each other. It seems like kind of a far distance to me, but we'd have to think about this. I mean, it's basically because this is the stopping distance plus 40%. So this is nearly 50% more distance than we really need between the cars. But basically you can see they're being consistent between the two. Basically they're following each other like cars on a train. So this logic seems to be working pretty well. I've had a couple of bugs happen off camera that I haven't quite figured out yet, but I think they have more to do with the center line generation than with the car's speed. So I'm going to keep looking into those, and I haven't been able to reproduce them consistently. But what I'd like to show you, I would like to show you how this works well. So what I've set up is another behavior for a test car. So this is a test car that varies its speed in order to test the reaction of the other cars. So this test car's speed is going to vary like the cosine squared of whatever time it is. So it's going to be speeding up to a maximum and then slowing down and then speeding up to a maximum and slowing down, etc. And so what I'm going to do is for this car, the one that was traveling more slowly, I'm going to turn on the test car option. And now what's going to happen is this car, the one that's highlighted up here, it's going to be traveling like the cosine squared of time. So this might be that the car is having to pick up and drop off passengers. It might be that there's stop and go traffic in front of this car. But this is a good test for this car's ability to match the speed of the car in front of it because this car is traveling at a varying speed. And lo and behold, we get that the car is slowing down and speeding up. You can see that in the prints of its speed here. It is speeding up and slowing down in such a way that it maintains a pretty consistent distance between the two. Of course, this one, it might be accelerating faster than this one. This one, it doesn't need to match the acceleration of the car. It just needs to maintain a minimum of that stopping distance and a preference of the following distance. And so this car is moving along. This one is adjusting its speed accordingly. And so this would be the scenario in which like I said, there might be stuff going on in front of this car, but this car is able to adjust accordingly. And so we keep traffic moving along while keeping our vehicles and therefore our passengers safe. There is one other scenario I would like to take a look at today, one other test I'd like to show. I have a third car, another car to be following. I've had it deactivated. I'm going to reactivate it. So this car, remember this car at the top is the one that's going to be varying its speed like the cosine squared. These two are programmed to match the speed of the car in front of them. And so what we're going to do is we're going to see what the effect is of this car speeding up and slowing down on our two cars behind it. What I'd like to do in the next video is get a whole bunch of cars in a loop. I'll probably need a bigger loop, have them traveling at constant speed, and then have a single car brake. And there's this claim made in CGP Gray's video, The Simple Solution to Traffic, that what that does is creates a traffic Ouroboros that pushes the braking back, basically pushes the traffic jam back along the loop indefinitely. So I'd like to see if we can reproduce that in the next video. This will be sort of a mini test of that. Okay, so what we've got is that our two cars here are looking ahead of them to try to figure out where they need, or what they need to be doing with their speed. This one is going to be speeding up and slowing down according to the cosine squared. Okay, so we're coming up along here where these two cars are about to be affected by the car in front. This is the car in front over here. I know it's a loop, but pretend there's a front. Okay, so we're about to hit the point where this car is going to be within the following distance of this car. So we know that this car will behave well. The question is, what will the third car do? Will the third car also be able to adjust accordingly? Because remember, each car is only looking at the car in front of it. So this one is only concerned about this one. This one is only concerned about this one. So as this one reacts to the one in front, the one in the back is reacting to the one in the middle. And it looks like they are behaving nicely. We've got this car getting ahead, because remember, this one is zipping along at the cosine squared function. These two are accelerating and braking accordingly. They both have, I think they are both set up as, oops, excuse me. Are they both set up to print? Yeah, they're both set up to print debug statements. So these speeds you see here is a mixture of this car's speed and this car's speed. So basically every other one is this one, and then the others are this one. But it looks like they're behaving pretty well. It looks like we are keeping traffic moving while maintaining passenger safety, which is a great thing. So this is, I think, one of the first big successes of this code, to try to convince people that that self-driving cars can, in fact, coordinate with each other on the road. So if you've got any friends or family that are reluctant to embrace the self-driving car revolution, this might be a good video to show them that, yes, we can program these things to interact nicely with each other. So I'm going to work off camera on the traffic Ouroboros to see if I can get that set up. In the meantime, if you've got other scenarios you'd like me to test, I by no means have tested all possible scenarios. So leave a comment below or tweet me at LetsCodePhysics, and I'd be glad to hear your suggestions for other scenarios to test for this system. So thank you so much for watching. I will see you next time. Bye-bye.